happy to welcome Sam Chow from Warwick, who's going to talk to us about Galois groups of random polynomials.
Great. So first of all, thanks very much to the organizers for running this wonderful series. I've really enjoyed the talks, and it's a pleasure to now speak. So I'm going to talk about Galois groups of random polynomials. This is joint work with Rainer Dittmann. Right, so let me start with some motivation. We know from the quadratic formula, cubic formula, and the quartic formula that polynomials of degree 2, 3, and 4 are solvable by radicals, which means you can write them using rational numbers and plus minus times divides, brackets, and radicals, which are square roots, cube roots, and so on. We know from the Abel-Ruffini theorem that this is not true for general quintic polynomials. There are quintic polynomials which are not solvable by radicals. And the question is, how often is a quintic equation solvable by radicals? So let's quantify this. If we have a reducible quintic polynomial, then we can factor it into 2 lower degree polynomials, and then it will be solvable. So let's just restrict ourselves to irreducible polynomials, and let's just take monic polynomials as well. So irreducible monic quintics, and let's say the coefficients go between integers between -h and h. So we can count how many of these are solvable by radicals. Now, in total, there are about 2h to the 5 polynomials here, and most of these are irreducible. So it turns out there are about h to the 4 reducible ones, and we show that the probability of being solvable is 0, but also there are very few of these solvable quintics. There are fewer of these irreducible solvable quintics than reducible polynomials. All right, so we beat the trivial bound by a long way, and we even show that this is a rarer property than being reducible. All right, but this is still probably far from the truth, because there are families of quintics you can construct, of which there are at least h to the 3/2 that are reducible up to height h. And in practice, the lower bounds tend to be closer to the truth, because it's hard to find efficient methods for upper bounding these quantities. All right, so I think that's a nice problem. So how do you study this problem? So solvability by radicals is a classical application of Galois theory. Okay, so reducible quintics are solvable. So now let's talk about irreducible polynomials. And we can define the Galois group of an irreducible polynomial over a field by taking the splitting field, so the smallest field extension over which it splits into linear factors, and consider automorphisms of the splitting field. And these form a group in composition. These form a group called the Galois group. And a Galois element will permute the roots. So we'll get a group action. We'll get an action of the Galois group on the n roots. So the Galois group will be a permutation group. It will be a subgroup of the full symmetric group Sn for a polynomial of degree n. And here n is 5 in the case of quintic polynomials. All right, so we'll get some subgroup of S5. All right, and there are some facts that are useful. The polynomial is solvable by radicals if and only if the Galois group is solvable. All right, and I've put the meaning here. There's a subnormal series with abelian quotients, but all right, we'll make everything. We'll have more concrete criteria, so it doesn't matter so much what it means at this point. Some property of groups. So we get some property of polynomials corresponds to some property of the Galois group. And also, the polynomial is irreducible if and only if the Galois group acts transitively on the roots, which means that if you have 2 roots, then there's an element of the Galois group that takes one root to the other root. Right, so in any specific case, when you fix the degree and it's small, say, then you get a very small number of possibilities for the group. So here's what happens in degree 5. The transitive subgroups of S5, that's the subgroups that act transitively on the 5 elements. Are these 5? To conjugacy, you can have the full symmetric group, you can have the alternating group A5. These are the even permutations, and then the 3 on the left are solvable. So this is AO5, this is the affine linear group. So this is a subgroup of size 20. You can think of it as AX plus B, where A and B are elements of the field of 5 elements, and A is non-zero. So affine linear transformations with coefficients in F5. D5 is the dihedral group of order 10, and C5 is the cyclic group. All right, so the ones on the left are solvable, and these are exactly the subgroups of AL5. All right, so we can detect the Galois group being a subgroup of AL5 using a resolvent. So a resolvent is an auxiliary polynomial whose factor type provides information about the Galois group of the original polynomial. And very typical resolvents will have a root if and only if the Galois group is a subgroup of some group. So in this case, the Galois group is a subgroup of AL5 if and only if the sextic resolvent has an integer root. It would normally be a rational root, but here it's monic, so the sextic resolvent has an integer root. So this is what we use. So the polynomial is solvable if and only if the Galois group is solvable, and then that happens if and only if the Galois group is a subgroup of AL5, and that happens if and only if the sextic resolvent has an integer root. Right, and here, yeah, B2, B4, B6, they're respectively quadratic, quartic, and sextic in the original coefficients, and delta is the discriminant. We also know what that is. All right, so this might seem like a complicated thing to check, but what we want to do is count solutions. So what we do is we introduce this integer root as an extra variable. And then the number of quintics that are solvable, the number of quintics that are solvable is bounded above by the number of solutions to this Diophantine equation that the sextic resolvent is 0. The variables A, B, C, D, E, and this new variable Y. So the upshot of this whole procedure is we've reduced the problem to counting solutions to a Diophantine equation. All right, and this is what we're going to do in general as well. So now we can ask the more general question of how often does each group occur as the Galois group of a polynomial? So solvable quintics was the same as solvable Galois group. We can ask the same question for any given group. Okay, so now let's fix the degree, at least 3, and look at monic irreducible integer polynomials of height at most h. Now the Galois group will permit the n distinct roots, so it will be a subgroup of the full symmetric group on n elements. All right, and so Hilbert's irreducibility theorem says that if you've got a polynomial in a bunch of variables and then you specialize some, and if it starts off irreducible, then 100% of the time it stays irreducible. And it's a consequence of Hilbert's irreducibility theorem that you get a more general Galois theoretic version, which in this case means that for 100% of specializations, A1 up to AN, you get Galois group Sn, you get the maximum number of symmetries. All right, so that means that the number of monic irreducible non-Sn polynomials is little o of h to the n. So the total is 2h to the n. Right, so we know it's rare for the Galois group to not be Sn, but can we quantify this further? So van der Waerden in 1936 proved an effective version of this. So instead of this little o, so yeah, he quantified this little o and got some tiny but tangible saving here. And this initiated the hard quantitative study of enumerative Galois theory. Okay, then, all right. So this is very far from the truth. And van der Waerden conjectured that a lot more should be true. So conjectured that irreducible non-Sn polynomials should be very rare. So they should in particular be a lot rarer than reducible polynomials. So let's see what that means quantitatively. The number of reducible polynomials is about h to the n minus 1. I guess you can get these by taking out a linear factor. You can get this many, but there's some constant here, some positive constant times h to the n minus 1, which gives an asymptotic formula for reducible polynomials, monic reducible polynomials with coefficients between minus h and h. And yeah, that constant depends on the Riemann zeta function. And Taylor proved this in 1962 without providing an explicit error term. So the error term is usually big O of h to the n minus 2. But there's a special case where you have a cubic that factors into 3 linear polynomials, and then we need this extra log h squared factor here. Okay, so Rainer and I provided the details of this in an appendix of our first paper. All right, but it's roughly h to the n minus 1. And I think a natural interpretation of van der Waerden's conjecture is that the number of irreducible non-Sn polynomials is little o of the number of reducible polynomials. Little o of h to the n minus 1. Okay, so that's what this talk is going to mostly be about. So Phyllis Lefton proved a weak form of the cubic case of van der Waerden's conjecture, getting h to the 2 plus epsilon instead of a little of h squared. So sharp up to an h to the epsilon fudge factor. And then Wang proved the weak form of van der Waerden's conjecture in the quartic case, assuming highly conditionally, so assuming the ABC conjecture and the Birch-Swinnerton-Dyer conjecture, and also the generalized Riemann hypothesis. Right, and in higher degrees, Dittmann had gotten h to the n minus 2 plus root 2 plus epsilon. So yeah, my co-author had improved this record of van der Waerden, Knobloch, Gallagher, and Zavina. And then in our first paper, we proved the quartic and cubic cases. So we actually proved the quartic case way before we solved the cubic case, even though the cubic case was actually, the quartic case was actually harder, but we were stuck somewhere in the cubic case, and eventually we got that as well. And in that work, we also, so we looked at all the groups individually, and we got the order of magnitude for D4 quartics being h squared log h squared, which is the only known case of the order of magnitude of a specific group other than the full symmetric group. Oh, there's a question. What evidence did van der Waerden have for this conjecture? Yeah, I guess van der Waerden didn't provide evidence, so I don't really know. I will talk about, you can nowadays we can get empirical evidence, and back then you could still get some heuristics. So I will mention a heuristic soon. You could conjecture this heuristically. In fact, you could conjecture much more heuristically. Yeah, so we got the order of magnitude for D4 quartics. And we beat h squared by a lot for in the cubic case. So yeah, indeed the exponent is much smaller. In the cubic case, we got h to the 3/2 plus epsilon. And actually this was improved. Yeah, this was improved a lot by Stanley Chow. So he got in the end bigger of h times log h squared, which is getting very close already to the lower bound of h. So yeah, so actually the exponent is 1 there, which dramatically beats the van der Waerden exponent of 2 minus epsilon. Yes. Yeah, the log of h squared. And so there's just the log squared gap remaining in that problem. Because A3 is the only subgroup of S3, transitive subgroup of S3 that's not S3 itself. And the lower bound is H. All right, but today I'm going to talk about higher degrees. So I'm going to introduce notation for a specific group. So a subgroup of the full symmetric group. For any subgroup of the full symmetric group, we can define the number of irreducible polynomials that we're counting with that Galois group. And call this NG. And then we can handle any group that's not the alternating group. So we can handle everything except the alternating group and degrees 7, 8, and 10. And apart from that, we prove van der Waerden's conjecture. So the way I've written it here is assume it's true for the alternating group, then we get van der Waerden's conjecture. So this degree condition might look a bit strange, but basically what happens there is we handled degree 3 and 4 already. Degree 5 was what I showed you with solvable quintics, and then degree 6 is a little bit more complicated. But basically we look at the solvable case and then some in solvable case, we do something quite specific. And then we have some general method that works. I mean, it will also work in degrees 7, 8, and 10, but it's more effective when the index is large. And what happens when the degree is 9 or at least 11 is that if you have some transitive subgroup that's not Sn or An, then the index is at least 217, and that's enough to break the Van den Waerden threshold. To get littler the number of reducible polynomials. And we also get a power saving on this littler. All right, so it seems that this is a hot topic because we released this on the archive a few weeks ago, and since then there's been loads of other work. Very shortly after we released our paper, this other paper got released that we didn't know about until we released our paper. So this was an AIM project between these 6 authors who look like 8 authors. It's Anderson, Gaffney, Lemke Oliver, Larry Duda, Shaken, and Zhang. They improved Reiner's result. So they got basically they looked at the alternating group and improved it there. So they got a better inequality for the number of irreducible non-Sn polynomials. So this is like n minus 2/3 as opposed to n minus 1 plus n minus 2 plus root 2. So this is about n minus 1 plus 0.33 instead of 0.41 or whatever it is. And
so this result is new only for the alternating group? Is that right?
Yeah. So I think the method worked for subgroups of the alternating group. So maybe it was sort of new there, but like we also have something in our paper that deals with proper subgroups of the alternating group. So this is mostly I would say this is only really new for the alternating group. And for the alternating group, that's completely separate to what we do. We do everything except the alternating group.
If the group is a subgroup of the alternating group, do you expect it to be the alternating group, or are there other candidates? Most probably.
It was a subgroup of the alternating group. Oh, in truth, probably. I would say, probably it should be the alternating group, but I don't know. I haven't thought about it so much, but certainly in terms of what we can prove more for subgroups of the alternating group, proper subgroups. But also, a couple of days after our paper was released, Bhargava announced that he'd proved, announced in the number theory web seminar on the occasion of Tanzaghia's 70th birthday, that he could prove the weak form of Van der Waerden's conjecture. So that he could prove big O of h to the n minus 1 plus epsilon. And he also expressed optimism that he could get rid of this epsilon to get big O of h to the n minus 1. Which would be Van der Waerden's conjecture up to a multiplicative constant. Okay, so I said I'd give some heuristic. So you can see that the alternating group is the hardest case. And it's a great struggle with the alternating group. But actually, we don't expect the alternating group to be very common at all. We don't even expect it to be the second most common. Not by a long way. So let me give you a heuristic a heuristic that I should say is very well supported. Well, it has some support. It's supported by everything. It's consistent with everything we know about the problem. All right, so the sort of key feature of AN polynomials is that they have square discriminant, and that's also true for subgroups of the alternating group. All right, and irreducible polynomials with square discriminant, yeah, we expect to be the alternating group most of the time. And all right, so let's look at this condition then of having like non-zero square discriminant. The discriminant's a polynomial of degree 2n minus 2 in the coefficients. And so we can look at this as a Diophantine equation, look at discriminant equals y squared as a polynomial in a1 up to an, and this new variable y, the square root of the discriminant, the square root of the discriminant, and try to guess how many solutions there will be. There's something called the naive heuristic from Diophantine equations, which is very often correct, although it could be incorrect because the degree is sort of high here, but it is very often correct. And what this says is you think about all these variables as sort of being random. You look at all of them, and then you try to figure out what should the probability be that discriminant y minus y squared is 0. So the way you do that, you look at the maximum possible value that polynomial could take, and you say assume it's random in the range up to that value. Okay, so if you do that, it could be as large as h to the 2n minus 2. Because the discriminant has degree 2n minus 2 in the coefficients. And so yeah, maybe the probability that discriminant equals y squared is 1 over 2 h to the 2n minus 2. And then the total number of possibilities for a1 up to an and y is h to the n plus n minus 1. And then, yeah, so then with this sort of random model, you'd get h. So you know, the cubic answer is about h, and the quartic empirical data is also about h.
Sam, sorry, regarding this, I found recently a paper of Frank and Thorn and Landermaster, sorry, I don't know how to pronounce their names, that gives a lower bound which is much bigger. And it goes
really?
back maybe to Hilbert, yeah.
What does
Because if
this is Frank?
I'll tell you, Aaron Landesman, Robert Lemke Oliver, and Frank Thorn.
Landesman, Lemke Oliver, and Thorn. I think I know this paper, but
yeah, and if you read, yeah, but their argument actually gives this model, a lower bound in this model, and it goes back, I think, the idea to some, it goes a lot back.
The thing is,
and it gives, the thing is that the discriminant has a lot of symmetries. I mean, unfortunately, I managed to get a better lower bound, but then I found it in their paper.
Really? I'll have to check this because I've looked at their paper and I thought they used a different height.
Yeah, but it's still, I mean, but if you take the tools, it gives this one. But I mean, the point is that the discriminant has a lot of symmetries, and you can exploit it to get h to the n over 4, something like that.
H to the n over 4?
So sorry for the interruption.
No, thanks very much. No, I appreciate it. H to the n over, so you think the method gives h to the n over 4, even with this height?
Yes.
Okay. Okay, that's not what I thought.
Me neither.
So I'll have to check. I mean, that's not what I thought, but also reading the paper, that's not what I thought. But I'll double check it.
I mean, for example, if n is 0 mod 4, and you take a polynomial such that f and plus f prime is a square, then the discriminant will be a square.
If f and f prime?
F plus f prime equal a square.
Yeah. Then
you have a lot of polynomials like that, and their discriminant will be a square. This is not what they do. This is a different approach. But they have a different approach.
They have a different approach.
Yeah, that you approximate f prime to a square or something like this.
Okay. So they have a different approach, but you're saying that if f plus f prime is a square, then you can also get many polynomials.
This was our approach, but then we found out it gives roughly the same lower bound.
Okay. All right. I'll check that out. Thanks very much, Leo, for telling me this. I really hope it's not true, to be honest, because my student proved this lower bound, and it was a really clever proof. So my student Nuno Rawala proved this lower bound, and yeah. But we'll have to check.
So maybe I'll write it up and send it, and maybe I'll find a mistake.
Somehow I really thought this was the answer. Okay, but maybe not. So yeah, maybe I'll check it, and yeah, if you could send something, that would also be helpful. Okay, thanks, Leo.
Yeah, I'll send you something written.
Good. So let's anyway. Still, the answer is probably much smaller, because in practice you very rarely observe AN polynomials, and it's not the largest in degree 4, and we don't expect it to be anywhere near as large as h to the n minus 1. Okay. All right. So they're the results, and so now I want to talk a bit about the methods. So we're going to do the same thing as in the quintic case. So there are these resolvents so we saw the sextic resolvent, and in general there are these resolvents for any group. And if the Galois group is G, then there's this resolvent attached to G, and it has an integer root. So then we introduce this root as an extra variable, and it remains to count solutions to the resolvent being equal to 0 with this extra variable and a1 up to an. All right, so this is an equation in many variables. So how do we count solutions to it? What we do is we fix all but 4 of the variables. So we fix a1 up to n minus 3. That leaves us with an minus 2 and an minus 1 and an. And y. So we'll call these a, b, c, and y. And so we'll get some equation in 4 variables. And generically, we'll get an absolutely irreducible threefold. And I probably won't have time to talk about the degenerate case where this is not absolutely irreducible. But basically, because of the way that this is constructed, we can use the Galois group to show that it's absolutely irreducible if and only if the polynomial is separable in y. So we can basically write it as a product. If we write it as a product of 2 things, then if we take a root of the first polynomial, we can also show that it's a root of the other factor, contradicting separability. So there are not that many exceptions to this. It's just where the discriminant of G is 0. So where G is inseparable in y. So now we fixed a1 up to an minus 3, and we've gotten some absolutely irreducible threefold. And we want to work at that level of generality. And also the polynomial has high degree in y. So it has degree d in y. So d here is the index. Okay, so absolutely irreducible polynomial with high degree in y, but there are still these 4 variables, and there's still a very general situation. And also our polynomial, now that we've fixed n minus 3 of the coefficients, the polynomial has large coefficients now. A1 up to an minus 3 are large, so this polynomial now has large coefficients. So we need a technique that works to count integer points varieties with and the defining polynomials have large coefficients. So we want a method that's uniform in the coefficients, in the size of the coefficients. So we can use the determinant method. This was pioneered by Bombieri and Pilar to count integer points on planar curves in 1989. And since then, there's been a lot of really great work on the topic. So generalizing and proving good quantitative results, especially by Heath Brown and Selberger. All right, so we'll use the result of Heath Brown's. So this is Theorem 15 of his published Chitaro lecture notes. So this says that if you've got this threefold, you can cover the integer points up to a certain height by a controlled number of surfaces. And these surfaces look like G equals Gj equals 0. So we have an extra condition that Gj equals 0 for these surfaces. And also Gj is co-prime to G. So this genuinely lowers the dimension of the variety from 3 to 2. So now we have 4 equations in 2 variables. Right, so we covered our integer points on the threefold by a controlled number of surfaces. And then we still need to count points on these surfaces. So we need to check if we've lost anything. So first of all, what we can do is we can eliminate the long variable, taking a resultant, and then we get some polynomial in A, B, and C, which go between -h and h. And then we're just counting solutions to f, A, B, C equals 0 with ABC between -h and h. And the thing that we've lost is irreducibility. So we had something absolutely irreducible, and now we just have some general f. So we factorize it. We factorize it over the reals, and the motivation is to apply Pilar's theorem. So Pilar's theorem is if you have something irreducible over the reals, some 3-variable polynomial, and you want to count these integer points on the surface, you get some bound that depends on the degree. Right, and it improves with the degree. So actually this is already enough if the degree isn't 1. So if the degree is 2 or higher, we can apply Pilar's theorem. And the difficulty for us, the difficulty that we have to grapple with is if it's linear. So if there's some linear divisor of this resultant. All right, so now we look at this case. This linear, so we write it as alpha A plus beta B plus gamma C plus delta. And then we look in this family. So then our F looks like G0 plus AG1 plus BG2, where G0 is most of it, and G1 is this quadratic thing, and G2 is this linear thing. So this is what happens when gamma is non-zero. And when gamma is 0, then either beta is non-zero or alpha is non-zero, and we get something very similar and actually easier. So this is like the hardest case. And then we have this 2-parameter family of polynomials. All right, and we want to think about what the Galois group usually is in this family. And the way we do that is using a 2-parameter function field. So this sort of problem was studied before by Yoshida, Smith, and Cohen. So for instance, if you fix all but 2 variables and then look at the final 2 variables, you want to consider the Galois group over the 2-parameter function field, or you can have 2 of the other coefficients. Okay, but here we have like a general linear 2-parameter family of polynomials, and we can use their method to show the Galois group is Sn over the 2-parameter function field. Okay, and that method works over the complex numbers, but over the rational two-parameter function field, the Galois group is larger. So the Galois group there will also be Sn. And I'll sweep these tricks under the carpet, but we can we actually get a smaller number of solutions unless f is a multiple of a rational polynomial, and then we can assume that it's rational. And then we can clear denominators to assume that it's alpha, beta, gamma, delta integers. And then we can assume that GCD of alpha, beta, gamma divides delta. And then we can assume that alpha, beta, gamma are coprime integers. And they're also, we can assume that they're not too large. Otherwise, there will be fewer solutions by the geometry of numbers. So this method actually it's quite complicated and quite ingenious, I have to say. But I'll defer it to the end because we just followed their method. So what I want to talk about for the rest of this section is how to finish the proof. If you know that the Galois group over the two-parameter function field is Sn. So this is like some quantitative version of Hilbert's irreducibility theorem. So almost all specializations of A and B, you should still get Sn. But it's a little bit more subtle because previous versions of this Galois theoretic Hilbert's irreducibility theorem, like Cohen's, for instance, they're not sufficiently uniform in the coefficients of the polynomial. So here the polynomial has large coefficients, and in Cohen's work, for instance, there's the height of the polynomial to the big O of one factor. So that doesn't quite work. So we have to do something more uniform here. So we use these resultants. We have some polynomial like this with Galois group Sn over the two-parameter function field. And the resultant will be some polynomial in A, B, and Y now that we fixed A1 up to A n minus 3. And we can use the Galois theory again to show that this would be irreducible if it was separable in Y. And if it were irreducible, then we would be able to finish the proof, which I'll also get to. So what we do is we tweak it to make it separable. So I think this idea has existed for some time, but this family of resolvents was introduced by Castillo and Dittmann in a 2017 paper. So we allow flexibility in the powers here, EI instead of I, and we have weights WK, and we have this shift G. So this is just like very similar to the resolvent from before, but more general, like small changes. And this is an equally good resolvent, but we can use these to get a separable polynomial with sort of bounded sized, everything bounded sized changes. And that way we get an irreducible polynomial H. And then we want to count solutions to HABY equals 0, where H is irreducible. And A and B are bounded by H. So this looks like Peeler's theorem, except there's no bound on Y. So we can infer a bound of Y, which is something like H to the big O of 1, but it's certainly not bounded by H. So this is a lopsided box now. So what we do is we prove a lopsided version of Peeler's theorem, which would be false if we use the total degree. But we have that the degree in Y is large, so that's why we can prove this. The degree of Y is D, which is the index, which is large, and then we can prove this lopsided version of Peeler's theorem. And the total degree we just need to be bounded. So then you might ask, how do we prove this lopsided Peeler's theorem? So what we do is we specialize B. We want to get down to the case of curves. We specialize B, and then if we get something irreducible, if it stays irreducible, then we call that good B. it becomes reducible but no linear divisor, we call that bad, and we call it super bad if it has a linear divisor. So we specialize B. And what we need then is that most of the time it's good. So we want most specializations of B to stay irreducible. So then to do that, all we need is a uniform version of Hilbert's irreducibility theorem, like the one that actually involves irreducibility directly. Yeah, so again, our coefficients are large now. So we need sort of uniformity in the coefficients. So that's what we do. We prove an almost uniform version of Hilbert's irreducibility theorem. So yeah, we have a polynomial in a bunch of variables that's irreducible, and it has some, we look at the degree in the variable y. Then almost surely you get something that stays irreducible. And the exceptional set is something h to the epsilon plus a half. And then there's also some dependence on the size of the coefficients, but it's not too big. It's just some g to the epsilon. Whereas in previous versions, more general versions, as g to the height to the big O of 1. And yeah, and we need it to be g to the epsilon. Okay, then you might ask, how do we prove this? Well, okay, so we can reduce the s equals 0 case. And then we use even more general separable resolvents. So we have a very small number of variables, so we can get this to work if we once we've reduced the s equals 0 case. But what happens is it starts off irreducible. So it starts off with the transitive Galois group. And then when you specialize, it becomes reducible. So the Galois group becomes intransitive. So you get some subgroup of relative index at least 2. And then there are general resolvents which treat this, and when we can show that they have few solutions. All right, so that's a sketch of the proof. And I have, I guess, a little bit of time to talk about some other stuff that I swept under the carpet. So one thing is the degenerate case. All right, so I explained briefly why there are not so many tuples a1 up to an minus 3, where the threefold that we get in the remaining coefficients in y, that's not absolutely, in the remaining variables in y, that's not absolutely irreducible. And what do we do then? Because the trivial estimate is then still not enough. Then we use some information about the one parameter function field. So there's a result of my co-authors demands that if you sort of fix all but 2 coefficients and then you choose one more, so then almost all choices of that one more coefficient, you get some SN Galois group over the one parameter function field. So we use that to say that usually once you choose AB, you get Sn over the one parameter function field. And then we can use a separable resolvent, and we get some polynomial, we get some curve that's irreducible of high degree, and we can apply lopsided Bombieri-Pila. So we had to prove lopsided Pila, which was about surfaces, but lopsided Bombieri-Pila, which is about curves, already exists. It's already very nice lopsided Bombieri-Pila. So the other thing I didn't talk about was this method of Cohen, Yoshida, and Smith. So the Galois group over the two parameter function field is Sn. So how to prove this? So for a permutation group to be Sn, it's enough to show that it's doubly transitive and has a transposition. So doubly transitive means that if you take 2 pairs of distinct roots, then there's a Galois element that sends one pair to the other pair, one ordered pair to the other ordered pair. And doubly transitive is sort of the easier thing. So if n's at least 3, then there's an equivalent definition, which says that if you take it, the stabilizer subgroup of a point, then that acts transitively on the remaining points. And what this translates to is if you take out one root, if you factor one root out of the polynomial, then you want the remaining stuff to be transitive. So you want some irreducible polynomial. And we can basically prove by brute force that this doesn't happen. And we use like one of the trick involving transcendence. This is sort of a short calculation. And then most of the method is about showing that there's a transposition. So then there's sort of a relationship between cycle types of Galois elements and factor types of the polynomial. So in this setting, what we need to do is show that there's show that there's some specialization with factor type 1, 1, 1, 1 up to 2, and this would give us a transposition, something with cycle type 1, 1, 1, 1 up to 2. And this means that there's a double root, no triple roots, and no pair of distinct double roots. And we can get the discriminant to be 0, which means that there's at least a double root. And then we also want to know that we want A and B so that there's no triple root or two double roots. Okay, and with some quantifiers that I've written down here, there's some criterion for this in terms of the rational function G0 plus AG1 over G2. And this is about the derivatives of this rational function, solutions to Diophantine equations. And there are many steps, but basically the only way that it can happen, the only thing that can go wrong is for there to be two double roots. And then it turns out there's a very specific structure which involves composition. So they're basically all polynomials of some specific rational function of degree at least 2 with denominators cleared. This is the only thing that can go wrong. And we can show that we don't have this structure, basically. G0 and G1 and G2 don't have this particular composition structure. And finally, how does this come up? So there's a theorem of Lyros that says if you have a field that lies between some base field and the transcendental extension in one variable, then it's a simple extension. So you can use the base field and then adjoin just one rational function. And what that means is that any element of such an intermediate field is a rational function of this rational function. So this is how we get this composition, which leads to some contradiction and completes the proof. So thanks very much for your attention.
Thanks, Sam. Let's all unmute and give Sam a round of applause. So if anybody has any questions, it'd be great to hear some. I was wondering mainly about the lower bound. So is there a guess? Do you have a guess, or is there a standard conjecture?
I mean, we'll have to check because Leo seems to think that this paper of Landesman and Lemke Oliver and Thorne about AN fields also gives H to the n over 4 for this problem. You mentioned something about alternating group most likely not being the worst case. Are there some other known cases where it's? Oh yeah. So in the quartic case, it's definitely not in the quartic case. I mean, we could already see empirically that there are several groups that are more prevalent, but we could also prove that they're. Oh no! I guess we haven't totally proved this. So yeah, I mean, I guess to prove that it's not the most common, you would have to prove a good upper bound for AN, which isn't known. So I guess it's not like known in any case, but
No, but there are families of irreducible polynomials that have a h to the n over 2 naturally, like composition with quadratic factors. Let's say polynomials of even degree, such that all the odd coefficients are 0. And this gives you h to the n over 2. And it's not clear whether this dominates an or not, because as Sam had the intuition, me at the beginning also, that an should be h, but now I'm pretty sure. I gave you the example. I mean, f plus f prime being g square. I mean, it's an easy computation with resultants that the discriminant is a square there. So it's not clear to me what should be the guess for an. I don't know. I mean, I heard some people saying that the density, I mean, the number of an should be h to the n over 2, but they didn't give any good heuristic that I can understand.
Yeah.
And I can certainly understand the heuristic for 1 over h, but it doesn't take into account the fact that resultants are, discriminants have a lot of symmetries, like I mean, you can do GCD to I mean, you can write them as a resultant of 2 polynomials and then do GCD and other stuff. So it's not clear to me what is the right answer, and computer cannot help us, right?
No, well, I don't know. I mean, in the quintic case, the computer suggests that it's not very common. So, yeah, so D4 seems to be the most common in the quintic case, apart from S4. And then what are the other ones? So V4 also seems more common than A4 in the quintic case.
Does D4 correspond to this case where you have a polynomial of x squared?
Yeah.
Okay.
Yeah, in general, it will be the hyperoctahedral group, because the roots come in pairs, and the Galois group preserve the block structure of the pairs of roots. So it will be the Rith product C2 Rith product Sn over 2. And naively, I would guess that this is the most, at least when the degree is even, this is the most, the second group after, the second transitive group after Sn, but it's very difficult to prove anything, as some say.
So your methods, quite a lot of it just says fix all but 3 coefficients and look at this polynomial and the remaining 3 coefficients. Is that true? Apart from some, so we need to.
That's what we do for the general method. Yeah, I guess I didn't show the rest of what happens with solvable quintics, but for solvable quintics, for low degree, for instance, for degrees 5 and 6, say, we actually fixed all but 2 of these coefficients. That's another technique, and then we cover the surface by curves. I mean, it's, yeah, what matters is I mean, yeah, I guess you wouldn't know which one works better quantitatively unless you do both. But what happens in these lower degree cases is that we can eliminate the linear case. So we can show that certain varieties don't contain lines. And that gives that makes it more effective. But that requires that requires computer assistance. And it can't work for the higher degrees. Or at least we don't know of any like natural ways to prove that there are no lines. Yeah.
Does anybody else have a question? Well, if there are no more questions, let's thank Sam again.